All right, in this podcast, we're going to talk about mass spectrometry. Basically, I want to give you a little background and explain to you how to read them. All right, so basically, how does it work? So the spectrometer is going to separate ionized atoms or molecules. That means they have a charge by changing the magnetic field or the voltage. And essentially what they're looking for is for it to eject an electron. Now make sure you understand what this equation is showing us. It's showing us that we have a metal that is neutral, and then we throw an electron at it, and we end up with it ejecting an electron. So we end up with an extra electron being let off, and that metal now has a positive charge because it lost that electron. The ions need to be charged because the whole way this works is by the use of a magnet, and magnets charges are sensitive to magnets. We can control charges through magnetic fields. So there's 4 steps in the process of getting data off a mass spectrometer. First off, the sample is ionized, which means it loses electrons, becomes positively charged. Then it is accelerated through the use of the magnet, and then it is deflected, and then it is detected. So it's deflected means it's flung into the detector plate up here, and then at the detector plate, then it is the data is collected and put onto a little bit of a onto a chart that we're going to learn how to read. All right, here's another view of what's going on, but again, ionized, and then it is sent through the magnets, which accelerate it straight into the detector. All right, so here's an example of a spectrum for magnesium. Notice over here we have percent abundance. So that means that by looking at this and seeing where it meets up, like for example that one, we can assume about 80% of magnesium has a mass of 24. And so each line represents a different isotope. So in this one there are 3 isotopes. And so each line is an isotope. And then also note that, all right, also notice the length of the each of the masses. So the most prominent isotope has a mass of 24, and then we have about equivalent amounts of 25 and 26, which are super low. I mean, we're talking about 10% each, it seems, and then this one's 80%. So you can guess that the mass of the of magnesium should be very close to 24 because that's your most prominent one. So it's like if you make a 24 on all your tests, then your average should be really close to a 24, right? Of course, you guys make, what, 104s? All right, now this one wants us to draw a spectrum. We're given percent abundances, and then we're asked to draw a spectrum. So we have masses 204, 206, 207, 208, and then over here are our abundances. So first off, we need to get our axes of our graph straightened out. All right, so our axes of our graph should be percent abundance over here, and then our mass charge ratio down here. All right, now we want our percent abundance to run to 100, and then there's 50, right? That's our middle. And then, sorry for that brief interlude there. All right, so we know that our largest mass is going to be 208 down here, and then our smallest mass is going to be 204. And then we also have a 207 and a 206. And my scaling's a little off here. That's okay. All right, so the very lowest is the 204, so it's just 1.4%. So it's going to probably even be less than that. And then we got 206 at 24%. So that'd be like that. And then 207 is slightly less than that. And then 208 is a whopping 52%. All right, so there's a very rough rendition of a mass spectrum. All right, now relative abundance versus relative intensity. What's the difference? All right, so these are the relative abundance and relative intensity graphs for magnesium. So we're still looking at magnesium again. So over here, notice percentages, right? So if you have a sample, 79% of the sample of magnesium should have a mass of 24, okay? Over here, think of these as, think of them as just like sets. So say, for example, I had 100 atoms, okay? So 100 atoms in my sample would be mass 24, and then 13 atoms would have a mass of 25, and 14 of them would have a mass of 26. So if I wanted to determine my percentages from my intensity, all I'm going to do is I'm just going to say, okay, so I had 100 atoms that were mass of 24 out of 100 plus 13 plus 14, that's 127 total, and I would end back up with 79%. Okay, so you can go from intensity to percents very easily if you need to calculate the average mass. All right, here's a mass spectra of fluorine. Now, hopefully, you'll notice that fluorine's a little different. So, fluorine's average mass on the periodic table is exactly 19.00. So, see, here you see that. Now, what's so odd is there's a second peak that, if you'll notice, is double the mass. And if you remember a little bit about the diatomic elements, you remember that fluorine is diatomic, so it appears as F2. So on diatomic elements, you end up with two different things. You end up with lines or peaks for the monoatomic ions, meaning just by themselves, and you end up with peaks for the diatomic species, which is the more prominent. Now, in fluorine, there's only one true isotope of fluorine, fluorine 19, which when it becomes F2 in its diatomic form is a mass of 38. But in other ones, you have more isotopes, which makes for more possibilities for peaks. All right, so here's an example for bromine. Hopefully you remember that bromine is also a diatomic. So we're going to see some diatomic peaks, and then we should see some monoatomic peaks. So we have 2 monoatomic peaks, and then we have 3 diatomic peaks. All right, so we want to label each of them. So this one, number 79, peak 79, that's just a single bromine, and it has a mass of 79. And then here at 81, you have another single bromine with a mass of 81. All right, now here's your diatomics over here. So the one with the mass of 158 would have to be a bromine 79 attached to a bromine 79. All right, the 160 is going to be kind of like your dihybrid here. It's a bromine mass of 79 diatomic with a bromine mass of 81. And then the very heaviest one is going to be your bromine 81 with your bromine 81. Okay, so just note that they can be different depending on if it's a monoatomic, like a normal element, or if it's a diatomic element. And also remember with the diatomics, the more isotopes you have, the way more peaks you're going to have, right?